Hi, Namaskar. Welcome to the second lecture in the Vedic Mathematics series. Today, in this lecture, we are going to discuss a very important topic, that is the idea of geometry in the Sulba Sutra. So, for those who haven't watched the first video, they can go and watch the first video to know more about what Sulba Sutra are and more about where they are located, what is the history of these texts. I'll also give a brief introduction in this video. The link of the previous video will be shared below. You can also check the channel for it. So, basically, the outline of this lecture is going to be, we are going to begin with a very brief introduction on Sul Sutra, then we are going to move on a brief history of the Pythagoras theorem before Pythagoras was credited with discovering it. Then we will move on to the idea of Pythagoras theorem and Pythagoras triplets, and also how they are present in the Sul Sutra. Then we will move to the antiquity of the Pythagoras theorem in India. Then we'll move to a very simple and interesting proof of the Pythagoras theorem, which is what we suppose that the men who wrote the Sul Sutra used. And then we'll have a small conclusion to the video. So, without wasting any further time, let's get to the topic at hand. So basically, the Sulb Sutra are a class of texts that are embedded in the Vedic literature. They are a part of the Kalp Sutra. They deal with the idea of how to build Yagna Vedis. As you can see, these are the fire altars inside which Yagya or Havan is conducted. These are the kind of Vedis that are used, and it requires very sophisticated geometry and knowledge of advanced concept to be able to construct them properly. Also, these are like the map or the instructions to make it. These have been embedded in the Sursut in the form of texts, in sutra or in small poetic formulations. And this is a historic Vedi that is around 2000 years old, which was discovered in Uttarkashi district of Uttarakhand. So this is what we call as Sen Chitti, a fire altar that is used to conduct yagya, that is built in the form of a eagle. And this is how it looked in real life. I'm not going to deal with the history and all here. Can be found in the past video in which I have discussed about it in detail. The basic idea that I would like to convey today and why we are discussing it, that the Pythagoras theorem has been falsely attributed to Pythagoras, that is for sure. We are going to try to establish that the first time that the Pythagoras theorem was established in its theoretical form, in the form that we know today, with a probable proof, was in India around 2800 years ago, and not in Greece, and definitely not by Pythagoras. So, now let us get to the brief history of the Pythagoras theorem. So, basically, I hope that you are all aware of the Pythagoras theorem that we use a lot in geometry, the right angle triangle, in which the sum of the squares of the sides that enclose the right angle is equal to the sum of the hypotenuse. Or in school, that you maybe have learned that the sum of square of the base and height is equal to the sum of the square of the hypotenuse. Coming to the history of the Pythagoras theorem. So, before we come to the history of Pythagoras theorem, we also need to realize what Pythagoras triplets are. So, any pair of natural numbers or integers, positive integers, which satisfy this equation. That is, if a is one integer, b is a second integer, and c is the third integer, if it satisfies this equation, then it is a Pythagorean triplet. The simplest Pythagoras theorem, the simplest Pythagorean triplet is one of 3, 4, and 5. So 3 square 9 plus 4 square 16 equal to 5 square 25. So 3, 4, and 5 is a Pythagorean triplet. So we have evidence of Pythagorean triplets at least as far as 4000 years ago, which are found in Babylonian and Egyptian tablets. Uh, this 3, 4, and 5 triplet is found in a Chinese manuscript, which is called the Chinese Nine Sections, around 1100 BC. We also have evidence in Egypt, which is the Kahun papyrus, roughly 4000 years before the present, that is circa 2000 BC. There is also reference to other triplets. One of the most important references is one which is found in the Plimpton 322. So, this is a Mesopotamian tablet found in the Babylon region. This is dated around 1800 BC, around 3800 years from now. Also, there is another triplet that is 6, 8, 10. So 6 square plus 8 square equal to 10 square. This is found in the Berlin Papyrus 6619. Also another the artifact that was found in Egypt. So the idea of Pythagorean triplets was at least known to a lot of civilizations like the Babylonians, the Egyptians, the Chinese, and also the Indus Valley. And to us, this is something which we will surely discuss. But the problem is that the Pythagorean triplets, the knowledge of Pythagorean triplets do not imply the knowledge of the theorem itself, because Pythagorean triplets are basically very easy to find. You just take, if you are building something, you can just construct it in front of you and just measure out the side lengths and you will get a triplet. So basically, make one wall like this, make second wall like this, join them, and then measure the distances manually. You can get them. Knowing that does not mean that you exactly know that this holds or this theorem should hold. There should be a theorem which should link the three. You can just make a simple observation and be done with it. After this, we'll discuss how what happened in India, and the modern credit goes to this guy, that is Pythagoras. The problem is that there is unfortunately no proper historical evidence that Pythagoras ever discovered the theorem, because the writings of Pythagoras were mostly lost, and we get a lot of knowledge about him, including the Pythagoras theorem, from the text of the later authors. What is for sure is that the axiomatic definition of the theorem was known, that is something on which all scholars agree, in the roughly 300 BC era, that was by Euclid. So Euclid gave an axiomatic approach towards Pythagoras theorem for the first time. That is the modern scholarly consensus. However, we do not think so, because we have ample evidence that axiomatic definition and proof of the theorem was known to the Indian authors, which we will establish now. So, moving on to what do we find written in the Sulba Sutra. So, there are two or three Sulba Sutra that we know, one of Baudhayana, the other of Upstam, and also some others, which we will discuss later. There's one by Katyan also. Now, first we will move to a special case of the Pythagoras theorem that is mentioned in Baudhayana Sulba Sutra 1.45. What it says that, so this is a Sanskrit formulation, this is what is found in this sutra, and the translation is: the diagonal chord of a square makes double the area. So basically, if you have an isosceles triangle with, let's say, length L, the other with length L, then the diagonal will be square root 2L. Basically, L square plus L square, the root of that, the root of 2L square, that is root 2L. Now, obviously, L, if this is L square, this is L square, and this is root 2L. If you make a square on the diagonal, so the square will have side length of root 2L. The diagonal chord of a square makes double the area. So let us say you have a square and you have its diagonal. So the diagonal is same as root 2L. Now you make another square which has the side as this diagonal. That will have the side length of root 2L. So the area of this will be root 2L square, which is 2L square. So what the sutra wants to say is that the diagonal chord of a square makes double the area. Or if this is L, this is L, then this is root 2L. This is what the sutra basically says. That is, so this is basically the Pythagoras theorem for an isosceles triangle, because in a square both of the sides are same. That therefore it forms an isosceles right angle triangle, and we have the Pythagoras theorem, that is the diagonal chord makes double the area, or simply it is trying to say that the diagonal chord is equal to square root 2 times the length, or square root 2 times the A or L, whatever you take this to be. This is a special case. Then it also moves and says, in another special case, that is take a rectangle whose breadth is equal to the measure of the side of a square. The length is equal to its Dvikarni. So these terms Dvikarni and Trikarni, which when they appear in the Sulba Sutra, Dvikarni means square root 2, Trikarni means square root 3, Karni means the square root, and Dvi, 3 are the numerals 2 and 3. So If you take a rectangle whose one side is equal to L, that is L, measure of side, this is the breadth L, and its length is equal to Dvikarni, that is root 2L. Then the diagonal will be Trikarni, that is root 3L. So basically, if this is L, this is root 2L, then by the Pythagoras theorem, we have this is equal to root 3L. So this is another special illustrated case of the Pythagoras theorem in Sulba Sutra, and also what does it illustrate? It illustrates the Pythagorean triplet of 1, square root 2, and square root 3. Now, what is interesting is, as just recall that when we talked about triplets here, we talked about the triplet 3, 4, 5, 6, 8, 10 that are found in the Chinese as well as in the Egyptian and Babylonian manuscripts. They are all integral Pythagorean triplets which can be observed, which can be again observed through construction. But this case of 1, root 2, and root 3, which is found in the Sulba Sutras in India, is an irrational Pythagorean triplet. It is not right to call it Pythagorean triplet because they are not strictly integers yet. So, if you want to mention this, what they have mentioned, that is, this is L, this is root 2L, this is root 3L, you cannot do it by measuring the sides or constructing it. You need to know the Pythagorean theorem, then you can construct such a triplet. This is another point, that for the first time, irrational sets that represent the side lengths of a right angle triangle were mentioned in the Sulba Sutra. And then we have Baudhayana Sulba Sutra 1.49, which deals with a lot of triplets. So in this, the triplet 3, 4, 5, 12, 5, 13, 15, 8, 17, 7, 24, 25, and one more triplet which we will discuss a bit later. They are mentioned in here. So because so many triplets are found in one sutra, it is now amply clear that the makers and the writers of the Baudhayana Sulba Sutra had a fair idea of what Pythagorean triplets are conceptually, and not as random guesses through construction. Then we move to the idea of the first time the Pythagorean theorem in human history was recorded in a text in its form as we know today. This is that sutra, that is Sul Sutra, Baudhayana Sul Sutra 1.48, which mentions that the diagonal of a rectangle produces both areas which its length and breadth produces separately. That means that if you construct a square on the diagonal of a rectangle, thus the area of that square will be equal to the sum of area of a square made on its length and a square made on its breadth. Or if this is L, and the area of the square based on this will be L square. If this is B, then the area of a square which takes this breadth as side will be B square. And if there is a diagonal which is C, then the square will be, the area of the square taking that as side will be C square. So A square plus B square equal to C square. This is what this sutra goes on to say, which is the same as Pythagoras theorem in other words. So this is the first time in human history that was recorded in India around at least 3800 years ago that we have the Pythagoras theorem in its theorem format, and this is at least 400 years before Pythagoras was born. So what is fundamentally established is that it is absolutely wrong to at least attribute it to Pythagoras, because we have clear evidence of the theorem as it is, at least as Pythagoras mentioned it, because Pythagoras did not give any axiomatic definition if you go by that construct. Hence, before, because it was known at least 400 years before Pythagoras was born in India by the writers of the Sulba Sutra, henceforth, it is right to call it something like the Sulba Sutra theorem, or you may attribute it to Bodhan. We cannot exactly attribute it to Bodhan, because there are two other Sulba Sutra which mention the same thing, that is in Katyan Sulba Sutra 6. Sulba Sutra 2.11, and in Apstam Sulba Sutra, that is in Apstam 1.4. So there are three Sulba Sutra which basically mention the same statement, at least 400 years before Pythagoras was born. So we have established this fact. Now what we will establish is that there is an interesting proof for this, which the Sulkars may have known. The problem is that the Sulb Sutra are basically manuals. They are manuals for constructing the Yagyavedis and all. So they go on to give you the methods and theorems. They don't delve into any proof because mostly that is outside the ambit of the text itself. So we will go to the proof. Before that, we will discuss another important area, that is the antiquity of the Pythagoras theorem in India. So was it for the first time 3800 years before the present day, or was it known even before that time period, in the Vedic era, in the era of the Brahmanas and the Upanishads, etc.? Well, what we what I would like to argue is that they were known in that era of the, at least the Brahman text, that is Shatpat Brahman and all. What is that era? That is roughly 4000 years before today, that is in 2000 BC, contemporary to the Babylonians and Mesopotamian tablets, or maybe earlier than that. How do we go to establish it? So now, this is a very special kind of Yagyavedi, which is called the Mahavedi, which is used in Vedic Yagya. Now, notice that this is how a, so in modern day, when you look at yagya and all, what we see is a square havan kund in which yagya is done very simply. That was not the case in the Vedic period. The yagya in the Vedic period was an extremely elaborate ritual in which the idea of making uh you know the fire altars, yagya kundan, etc., for yagya was precisely measured, precisely geometrically prescribed in the text. So this is how that formation used to look. So this is the Mahavedi, that is the great altar space inside which the yagya will take place. Inside this, there is your Som hall, Havidharan, and the Chitti, or the altar that I showed you before. And then there are other components of the yagya. So yagya was a very elaborate and very expensive ritual at that time. Now this Mahavedi, the dimensions of this Mahavedi are also mentioned very clearly in the Brahmana text, that is in the Shatpat Brahmana. What Shatpat Brahmana says is that this is the dimension that has to be there. What I want to mean is that to construct this trapezium, that is these dimensions, you need to have knowledge of this Pythagorean triplet. Okay, this Pythagorean triplet, that is 36, 39, and 15. If you have this Pythagorean triplet, that is 36, 39, 36, 39, and 15, that is this triangle, you can construct this trapezium easily. Else it is not possible to construct it. So this triplet, that is 15, 36, 39, was known in 4000 BC era. 39 square is equal to 36 square plus 15 square. This is also mentioned here in this, which I skipped. So this part of this deals with the Pythagorean triplet 15, 36, and 39. So also, why can we be sure that they knew this triplet? Because this Mahavedi is not only mentioned, but it has also been mentioned that how to construct this, at least to construct this 14 fold, that is, if this is the dimension, how to construct it for how to construct it when each of these dimensions are multiplied by 14. This is mentioned in Shatpat Brahma 10.237. This is at least 4000 years from the modern day time. So if you are able to construct this, and also you are able to increase the area to 14 times precisely for the 101st sacrifice, so the 101st ahuti that will be given when this Vedi will be 14 times, each dimension will be 14 times of this. So at least in that era, we had a fair idea of Pythagorean triplets in India, and most likely because that was a continued knowledge that was passed down, it is highly probable that the theorem was known in that era also. Also, there is another fire altar which is Dakshinagni, which is mentioned in Rig Ved. So in the Ved also, it is mentioned in that to construct that Dakshinagni, you need to construct a right angled isosceles triangle. And to construct a right angle isosceles triangle, you again have to need to have somewhat an idea of the theorem itself. So we can conjecture that it is very probable that these ideas were known even when the Vedic Samhitas were compiled, and the ideas continued down and were further refined and given a theoretical axiomatic definition in the Sulba Sutra. Also, see that this idea of this Mahavedi or the Pythagorean triplets, these fire altars are also found in the Indus Valley civilization, in the Sindhu Saraswati civilization. This is a picture of one of those fire altars. So the Indus Valley civilization or the Sindhu Saraswati civilization also had the idea of constructing such fire altars. So now these ratios in which this Mahavedi is constructed, this ratio is 12 is to 15, that is 5 is to 4. This ratio 5 is to 4 is also found in the fire altars of the Indus Valley civilization, and also in the outer castle walls, that is in the fortification of Dholavira. There also we find a similar 5 is to 4 ratio. So this ratio 5 is to 4 is also found in the Mahavedi, in the Shatpat Brahmana, and this is the same ratio which is found in the Sindhu Saraswati civilization, castles and other constructions. So there is definitely a link between the Shatpat Brahman text, the idea of this Pythagorean triplet and this Mahavedi, and the idea of geometrical constructions in the Sindhu Saraswati civilization or the Indus Valley civilization, which means that all these ideas basically of the Pythagoras theorem, the Pythagorean triplet, the Mahavedi, the fire altar are what is link a common link between the Sindhu Saraswati civilization, between the Ved, between the Brahmanas and the Sulba Sutra. By this, we can also say that the Sindhu Saraswati civilization and the Ved and the Vedic ideas were but two facets of the same civilization. One is the material facet, that is the fire altar, the archaeological discoveries, and the other is the literary aspect, that is the Ved and Shatvat Brahman, etc. Contrary to what the modern scholars argue about the Aryan invasion and all, this is a very strong counterpoint against that idea. Now we go to certain geometrical mathematics of this debate. So, how do you prove the Pythagoras theorem? This is one method that we are going to show today. So, this method that we are showing today, this is also found. So the proof of, at least for the isosceles case, is found in the Katyayana Sulba Sutra. So, this formulation is found in the Sulba Sutra. The second one we infer, or basically we try to claim that that is what they might have done for proving or deriving the theorem. So, this is a very simple idea, that is, in the Sul Sutra we find that you can construct this, what that is, what that is a square of area 1 unit, but what this square is, it is tilted at 45-degree angle. So you take this square and then you tilt it like this. So this is that square, tilted square. So how do you make it? The Sul Sutra says that just make a square of area 2, cut off middle points, join them, and you get it. That is very simple, because if this has an area of 2, if you know the Pythagoras theorem, you will know very easily that if this is side length A, its diagonal will be A. If its diagonal will be A of this square, then its side length will be A by root 2, and the area will be A by 2. So if this has area of A, then this has area A by 2. If this is a square of area 2, this square will be of area 1. So if you want to construct a square of area 1, which is not like this but like this, if you want to rotate it, basically you just make a simple square, take them, cut off the midpoints, join them, and you get it. How do you prove the Pythagoras theorem for the isosceles case? With this, very easy. You just observe that this is your square. Notice that if you complete this square, that is, if you complete this, that is this square, notice that it is very simple to see that this has area. If this square has area A, then this will be area A by 2. Now if you complete this completely, you can observe very simply, you can observe that if this has area A, this is area A by 2. Then if you complete this whole square, then you can see very simply that this figure will have area half of the area of this whole square. Or you are getting back at the same point, that is, if this has area 2, then this has area 1. That is equivalent to saying the Pythagoras theorem either ways. A very simple proof for isosceles triangle case, and it is very trivial also. What is an interesting proof is in the case where you have to generalize it. So to make you understand better how do we prove it, we first will do it with a case in which we will take some dimensions, some units, and then we will move to a generalized definition. Let us take the case of a simple dimension, that is, see, this is a square. This square, each side has length of 4 units. 4 units. And then what you do is you divide this into 4 parts. So 1, 1, 1, 1. So 1 unit each. 1 unit each. That is, divide the side equally into 4 parts. Join this like this. So the first point from here, the third from here, the third from here, the third from here, like this. So you join this. We can very easily see that this is also a square, just another tilted square. Like, if you would have joined these points E, H, G, and F, you would have gone to the same past problem, that is the same as isosceles case, 45-degree square tilted. This is somewhat tilted at some other angle, but this is also a square, IOGK. Now obviously if each side has length of 4 units, then the area of this square is basically 16 square units. Notice that now we have to just find the area of this square inside. How do we do it? So this square, that is QRST, the area of this square will be 4 square units because each has a side length of 2. QRST, this is 4 units. Okay. Now notice that if this is QRST, right? Now if you take this triangle IQK, this triangle IOT, this triangle OMS, and this triangle, that is MRK. So the area of this square plus this triangle plus this triangle plus this triangle plus this triangle is equal to the area of this whole square. Let us see it once again. The area of this square plus this triangle plus this triangle plus this triangle and plus this triangle. That completes the square. This is 4, and you are able to see that this triangle and this triangle, all these 4 triangles are exactly same. There is no difference between them. Just find the area of one of these triangles. How you'll find it's very easy. This has side of 1, this has side of 3. And the area of the triangle is half into base into height. That is, this is 3 by 2. This is 3 by 2. This is 3 by 2. And this is 3 by 2. So basically, each one of these triangles has area of 3 by 2 units, and 4 of them will have the area of 6 units. So if the sum of these 4 triangles is 6 units, the area, and this is 4 units, the total area of IOMK, that is the square, is 10 units. What is the insight that we get? The insight is that if this has an area of 10 units, then the side length is root 10. What is this side? This is 3. What is this side? This is 1. In this right angle triangle, what? 1 square plus 3 square equal to root 10 square, that is 10, which is again Pythagoras theorem. So we have very simply proved the Pythagoras theorem. That is we showed that the area of this triangle is 10 square units, which means that this is root 10. What we showed that this is root 10 when this is 1 and this is root 3. This is a simple case in which we have proved for a simple Pythagorean triplet 1, 3, and root 10. Well, the interesting point is that with this construction, you can just generalize it and prove the Pythagoras theorem generally. How? Let us say that IQ is A. This is A, and QK is B. Now this is general. This is just a general side length. So what we are trying to say is take this square and you can cut it anywhere where you want. Forget about this grid. Just this can be any square. Just take a side, but symmetrically, that is. If you are taking this at a distance of d, then you have to take this also as d, this also as d, as this also as d. You can construct another square. Let us say the square will be somewhat like this. This and this. So, I mean, rotate it a bit more or a bit here there, but you can rotate it however you want, however, at whatever angle. So you can make any possible square, any possible combinations of these side lengths, which makes it a general case. In that general case, let this be a and this be b, any arbitrary lengths a b. In this case it was 1 and 3. Now you can take it to be any a and b. If this is a, this is b. Notice that if this is a, then this is also a. Exactly similar, because the entire figure is symmetrical. If this is a, then this is, and this is b, then this is b minus a. If this is b minus a, then the side length of this square is b minus a. That is the area of this square QRST is b minus a whole square. Now the area of ITO, this again, this triangle has to be calculated. Very simple. This is b, this is b, and this is a. We have taken it as such, so this is half into AB. And 4 of this triangle, the area will be 2AB, that is half AB into 4. So the total area of IOMK for any general square that we make here, that will be B minus A whole square plus 2A plus 4 plus 2AB. That is A square plus B square. There is a small misprint here. It should be A square plus B square. Okay, so this square has area of A square plus B square. This is A, this is B. See that we are done. If this is A, this is B, this square is A square plus B square. So that is what the Pythagoras theorem is. A square plus B square. In a right angle triangle, the hypotenuse will be A square plus B square. So we have proved it for a general case with the same ideas at hand. Proceeding, So this is how you create, how you develop proofs in geometry. You think about how what can be done. You try to do it for a known length elementarily, and then after you have a idea of how do we do it for a create a grid and all, take a simple case. After that you can take it to a general case and complete the proof. This is the same idea that must have been used in that era also, and that is even today used if you want to make new proofs, create new and innovative proofs for geometry. This is just one idea. In the next lecture that we will do, then I will discuss another proof. I didn't want to do it in this lecture because it was a bit geometrically involved and tedious, where we will discuss the idea of how do we sum, that is, if you have a square of area A, another square of area B, you have to construct a square that has the area as the sum of these two areas. So how do you do it? It's an interesting geometrical problem. You have to construct it now. Construct it. And by construction I mean you don't have to do any algebra. Just do some construction that you do with compass and protector and just build it. So this is something which is again discussed in the Sulba Sutra. How do we construct a square or same as the area sum of the squares? How do you construct a sum that a square that is of the area of the difference of two squares, that is a minus b? These ideas have been discussed in detail in the Sulba Sutra. And with that sum of squares, we can also develop a proof of the Pythagoras theorem. That is a bit geometrically involved. We will discuss in the next video. Okay, so what are the conclusions that we draw from this video? There are few takeaways that I would like to mention. The first of them is that obviously the Pythagoras theorem has not been discovered by Pythagoras. We call it the Pythagoras theorem because that is what we have been taught. Definitely not discovered by Pythagoras. Pythagorean triplets known at least 4,000 years before, known in the Babylonian, Egyptian and Chinese texts, and also as we have shown, it may be inferred that they were known in India also in the Shatpat Brahmana and the Brahmana layer at least. So at least 4,000 years before, in China, in India, in Babylonia, and that is Babylonia, Mesopotamia, and in Egypt, four civilizations, this idea of Pythagorean triplets was amply clear. The first time that the Pythagoras theorem was mentioned in its theorem format, that is a square plus b square is equal to c square, was in the era of Sulba Sutra in 800 BC. That was 400 years before Pythagoras. So there's no point that Pythagoras should be credited with the theorem. And the axiomatic approach, the proof was, as we speculated, it was known to the Sulbakars. So that was also known in India at least 800 BC. So if you have to credit this theorem for the first time in theorem format, it should be to the creators of the Sulba Sutra, to the creators who wrote the Kalp Sutra and Sulba Sutra, that is the Vedic rishis or the Vedic Sulbakars. That is the conclusion that we have by this study. And yeah, so that is all that we will discuss in this lecture. And I'll come up with another lecture on this to complete this idea of geometry of Sulba Sutra, geometrical ideas in Sulba Sutra. Then we will go into some more advanced geometrical formulations and details. And then in the third lecture, I hope that I can move to some concepts that are found in the later texts by Bhaskaracharya in his Leelavati and uh, Aryabhat, etc. So that will be the third video, which will be of the general mathematical geometry series of India. If you have the urge to read more about this, I would suggest that you can read the writings of. There's this book by Datta which discusses some geometrical ideas in India. There's also a book by T. S. Saraswati Amman, if I'm not wrong. Can search archive .org. There are other texts, but I don't think that you'll find it online. You'll have to go to a library and maybe search on that. Yeah, that will be about it. Thank you for your attention. Thank you for your patience.